that'll obviously help us, well, address any questions that you might have. Okay, right. Well, we will make a start then. All right. So we've just got to the end of the C4 chemical calculations topic. Well, the first half of it, and we're going to just do a little summary lesson. So if you have missed out on any of the lessons so far, doesn't matter, because we're going to sort of cover all the different skills and concepts in this one video today. So I've sent you some work, and like I say, I'm going to work through every single question so you can work through it at your own pace. If you can't be live in this lesson now, it does not matter. You can simply watch this video later once it's uploaded into the Google Classroom. Okay, so question 1 is as follows. It says that sodium reacts with oxygen to make sodium oxide, and you just asked to find the MR of sodium, oxygen, and sodium oxide. So the first thing you need to do is you need to make sure you know which is which of these things. So sodium, which of these 4 things is sodium? Well, that's sodium there, isn't it? It's just one sodium atom. So where do we find the mass of sodium? Well, we're going to have to use the periodic table. Okay, so I'll just hold that a bit closer. You can find sodium is just there by my finger, all right? And which number am I going to use for the relative mass of sodium? Well, the key will help you. Relative atomic mass is the top number, so I'm going to be using 23. All right, so simply sodium has a relative mass of 23. And oxygen then, let's find oxygen in this. So where is oxygen? So oxygen must be that or that. Hopefully you can see that it's that. So what is the MR of oxygen? Well, oxygen is O2. So I need to count how many atoms are actually in it. So there are 2 oxygen atoms. And again, if I go back to the periodic table, have a look at it. Where is oxygen? So I think oxygen is there somewhere. Hopefully you can see the top number there is 16. So 1 oxygen atom weighs 16. So 2 oxygen atoms weighs 32. Yeah. So the relative molecular mass, or the MR, or relative formula mass, they're the same thing, is 32. The last one is sodium oxide, so that must be the thing that I've not underlined yet, which is that. So what have I got in there? I've got 2 NAs, and I've got 1 O. So it's Na2O. And then again, I'm going to use my periodic table. Oh, thankfully I don't have to for the rest of this, because I've already got the bits and pieces that I need. I know that sodium weighs 23. I know that oxygen has a mass of 16. 2 times 23 is 46. 1 times 16 is 16. Add those together, 52. So the answer to the first 3 questions, 23, 32, and 52. Okay. Right, I'm just going to clear the board and we'll have a go at question 2. Right, so if you are watching this back later, obviously you can pause the video, have a go at the questions first, and then watch me go through the answers. Okay, so question 2 says, how many moles in the following? So we've got how many moles in, and we've got 3 different things to look at. So we've got, that's 2A, I, and B. So I is 21.3 grams of Cl2. II, 5.34 kilograms of AlBr3. And the final one, mass of 0.25 moles of sulfur dioxide. Okay, so the question's now set up. How do we go about solving this? Well, we're asked to work out number of moles in this. So how do we actually do that? Well, we need to know this formula triangle. And there's really only two formula triangles you need to be aware of at GCSE Chemistry. So this is the one you use most often. It's mass over Mr. moles. So Mr is the MR, that's just working out the mass of a particular compound or element. Moles is the number of moles, that is, and the mass is measured in grams. Okay, so what am I trying to figure out here? So it's how many moles. So I'm just going to highlight in the question what I'm trying to figure out. How many moles? So what is the formula for working out moles? Well, I'm going to cover it up in this triangle here. If I cover that up, moles equals mass divided by MR. So I'm just going to write that there. Mass in grams divided by MR. Okay, so let's look at the first question then for 21.3 grams of chlorine. So we've got a mass. So we know that it's going to be moles equals 21.3 grams divided by MR. So we need to work out the MR of Cl2. Well, it's just two chlorine atoms. So again, I'm going to go to my periodic table. Yep. And if you can see chlorine, just there, the mass of one chlorine atom is 35.5. So I'm just going to write that in there. So two of them is 71. So the MR of Cl2 is 71. I can then do my calculation and then hopefully give us a nice answer. So 21.3 divided by 71 equals 0.3. Okay, so 0.3 moles. And again, don't worry about, a mole is just a number. It is a very, very big number, granted, but it is just a number nonetheless. So a mole is just a number. It's a very big number, 6.02 times 10 to the 23. And if I know that I've got 21.3 grams of chlorine, I've actually got 0.3 moles of chlorine. Well, let's do the next one then. So again, I'm going to write my formula triangle, use a different colored pen. So moles equals, so we've got a mass, but be careful here. The mass is in kilograms, all right? When it needs to be in grams. So how do I get from kilograms into grams? You times by 1,000, okay? So you times by 1,000. So 5.34 kilograms is 5,340 grams, and that's the mass I'm going to use. Right, and again, now I need to work out the MR of AlBr3. So I'll do that working out over here. So what have I got in this compound? I've got 1 aluminium, I've got 3 bromines. So get my periodic table out. What does an aluminium atom weigh? So it should be there somewhere. 27. And bromine weighs 80, or has a mass of 80. 27, 80. So 1 times 27 is 27. 3 times 80 is 240. Add them together, 267. So the MR of AlBr3, aluminium bromide, is 267. So my calculation is 5,340 divided by 267. So 5,340 divided by 267, you get 20. Nice answer. So that equals 20 moles. So if I had 5.34 kilograms of aluminium bromide, I've actually got 20 moles of aluminium bromide. And this question here, this question B, we're actually now not looking at the moles, we're now trying to find out the mass of 0.25 moles of SO2. So how do you work out mass? I'm going to go back to my formula triangle. I'm going to cover it up. Mass is Mr. times moles. Yep, so mass yep. So, what do we have in the question? We've got a number of moles, but we need to work out the MR, before we can do this. So what is the MR of SO2? Well, let's do it over here. So we've got 1 sulfur, 2 oxygens. So again, I'm going to go to the periodic table. Sulfur and oxygen should be both in group 6 somewhere. So oxygen has a mass of 16, sulfur has a mass of 32. So the MR is actually 64. So I'm going to do that now. So now 64 times 0.25 should be 16 grams. So there are your 3 answers to question 2 then. We've got 0.3 moles, 20 moles, and 16 grams. Hopefully that walkthrough helped you through that. Okay, I'm just going to clear the board now, and then we'll have a look at question 3. I think we're going to need this triangle, so I'm going to keep that there, because it's a reacting mass calculation, which we did loads of a few weeks ago. So it says, what mass of bromine reacts with 2.3 grams of sodium? So the equation is what mass of bromine reacts with 2.3 grams of sodium. And that's all we need to know from the question. Okay, so again, first things first, with questions like this, what are you trying to find out? What is your finish line? What is your goal? So, what mass of bromine? That's what we're trying to figure out. So, which of these things, these chemicals, is bromine? It's that one there, the thing that only has Br in it. Anything else has sodium in it, which is Na. So that's our finish line. What are we starting with though? We must be starting with something. It says here we're starting with 2.3 grams of sodium. So which of these 2 remaining things is sodium? Well, hopefully you can see it's just this. Yep. And I'm going to set up my grid. How do we get to the finish line? So we're starting here. How do we know how much of that we need? So I'm going to set up the grid by going there, there, and there. Okay, so it's almost like a path to get to the final answer. And there are 3 stages, effectively. The first thing is you convert grams into moles. So these are going to be moles down here. Well, how do you do that? Go over to our triangle. To turn mass into moles, so cover it moles, you divide by Mr. On this side, we're going to go back up to grams, so you're going to times by Mr. And this bit here is the ratio of the reactants, or the 2 species that you're looking at. So what is the ratio of Na to Br2? It's the big numbers at the front. So what are the big numbers at the front? It's 2 to 1. So imagine that there is just a big 1 there. Okay. Now that lets us know something quite important, because whatever number we get here, we have to then divide by 2 to get to this number here. Because it's a 2 to 1 ratio, the number on this side must be half the value of the number on this side. So I'm just going to put a little operator there to remind me. So I'm going to divide by 2. And before I start doing any calculations, I'm going to work out the MRs of these 2 things. So what is the MR of sodium? Well, again, sodium is an element on the periodic table. So I'm going to have a look. What does a sodium weigh? We'll have a mass, 23. So that's 23. And then what is the MR of Br2? Well, Br2 is just 2 lots of bromine, and each bromine has a mass of 80. So the MR is 160. And if you set it out like this, even if you've made a mistake there, or there, you will still get error carried forward. So you can still get quite a couple of marks on these questions. But now I've got everything set up. I've got my operators, I've got the numbers I need to use. I can just follow the path from beginning to end. So let's give it a go. So 2.3 divided by 23 is 0.1 moles. Okay, so now 2-to-1 ratio, so I'm going to divide by 2. That's 0.05 moles. And then I'm going to go back up the ladder by timesing by the MR of bromine, which is 160. And you end up with the final answer, 8 grams. So don't worry about sort of, because I know you can't draw this on the Google Doc that I've shared with you, but if you just sort of like write the answer and maybe a couple of the calculations how to get there. So 2.3 divided by 23 equals 0.1. Divide that by 2 to equal 0.05. Times by 160 to equal 8. Okay, and I think we've got another one of these questions so I'll go out now in question 4. Okay, so I'll clear the boards, I'll write it up, and then we'll go through it again. So it's what mass of oxygen reacts with 280 grams of iron? All right, there is some more to the question, but I'll just leave it there. So we've got Fe, 2Fe plus 3O2. Okay, I think just 1 second. 2Fe, 3O2, 2Fe2. It must be 4Fe actually. I think there's an error to try and balance this correctly. Yeah, that's better. So there might be an error on your worksheet. So again, make sure that you actually corrected it. It's 4Fe plus 3O2. All right, but it's exactly the same. The equation is usually balanced for you anyway, and usually correctly. So don't worry about that too much. You can edit it on the Google Doc that I've shared with you. So what are we trying to figure out? What is our finish line here? So what mass of oxygen? So which of these 3 chemicals is just pure oxygen? Well, it's the one with those in it. There you go. So there's our finish line. And what are we starting with? Reacts with 280 grams of iron. So which of these things that is left is iron? Well, it's this one over here. Okay. Again, I'm going to set it my grid on my path. Starting here. I know these are going to be moles. Down here. That's going to be divided by MR, and that's going to be times by MR. It's always the same. Like I said, the hardest part of these questions is finding your finish line and identifying your starting point. Once you've done that, it's just the same. Start there, finish at your destination. Okay. So what is the MR of these things? So before I do anything, I'm going to put in a couple of things. So the MR, let's do these bits first. What is the MR of Fe? Well, the relative mass, the MR, is just the mass of one atom or molecule of that particular substance. So iron, it's not 4 iron atoms. We need to find the MR is just for the mass of 1 iron atom. So iron is in the transition metals, middle of the periodic table. There it is. Has a mass of 56. So that equals 56. Over here, the mass of oxygen, because it's O2, which is 2 oxygen atoms. We've done this already. Each oxygen weighs 16, so the MR is 32. And the final thing I need to get right is my ratio. And this is quite a tricky ratio now I've corrected it. Because the ratio of here to here, use these numbers, my red pen. Is 4 to 3. Yeah. So what am I going to do here? What am I going to do? When I get this number here, to go through here, what am I going to type into my calculator? Well, it's a 4 to 3 ratio. Simply divide by 4, then times by 3. Yep. So divide by 4 times by 3. That's the easiest way of doing it. So divide by 4, press equals, times by 3. Now let's see if we can't put all this together into one seamless calculation. So, starting with 280 divided by 56 is 5. 5 moles. Brilliant. Divide that by 4 times by 3, you get 3.75. So I know if I've got 280 grams of iron, that equals 5 moles of iron, and I need 3.75 moles of oxygen to react with it. So I'm over here now, and to get to the finish line, I'm going to times by the MR, which is 32, which is 120. Yeah, and again, if you've made a mistake at any point, there, or there, but carried out the procedure perfectly, you will still get error carried forward marks. Okay, there's another one of these later on, I think, but we'll do something different now with question 5, which is on atom economy. So again, I'll clear the board and we'll have a look at atom economy. Right, so if you watch the atom economy video, hopefully you found it quite useful. So it's what is the percentage atom economy to make tungsten from tungsten oxide? Okay, right, so we'll have a look. It is woe 3, 3H2. Right, so. Okay, so I'm going to use the same sort of technique, if you like, that I've used in previous videos like this. So, atom economy is what percentage of the atoms that we put in, or the percentage by mass of the atoms we put in, ends up in the product that we want. So what are we trying to figure out here? Okay, what is the percentage to make tungsten? We're trying to make tungsten. So we're trying to make that. That's what we're trying to make. We're actually getting water as a byproduct, so we're not going to end up with 100% atom economy, but exactly how much are we going to get? So it's what's in the purple circle divided by everything in the red circle, all right? Everything on the left-hand side. So it's what you want, circle your product, however much of it is, divided by everything that you start with. And I'm just going to make a list of everything underneath, okay? So we're going to use the MRs of these things. So what atoms have I got? I've got 1 W, I've got 3 O's, and I think I've got 6 H's in total. All right, and on this side, I've just got 1 W. All right, so I'm going to use my periodic table in a moment. I'm just going to put a bit of a divide in there so we don't get confused. So I need to know the masses of tungsten, oxygen, and hydrogen. So tungsten is there. You can see the mass is 184, hydrogen is 1, and oxygen, is hopefully you getting used to by now, is 16. So it's 184, 16, 1. 1 times 184 is 184, 3 times 16 is 48, 6 times 1 is 6. Add them all together, and you end up with 238. Yeah, that's about right. And on the other side, so I'm going to put that in a big red box. So that's the total MR of the reactants. And now I need the total MR of the product that I'm making. Well, I'm only making 1 of these. So it's just 184. And then I need to work out what the purple box is as a percentage of the red box. So it'll be, so percentage atom economy equals purple box, 184, divided by red box, 238, times 100. And again, you get error carried forward here as well. So if you made a mistake with either your red number or your purple number, it doesn't matter as long as you carry it forward into this equation here. So let's put all that together. So it's 184 divided by 238 times 100, 77.3%. Which is quite high, which is really good actually. So this is why we actually do this process in industry to extract tungsten, because tungsten is quite a useful material. It's got the highest melting point of any material on the periodic table. And it is a metal, so it tends to be quite strong as well. So that lets us know that if we were to put in 100 grams of starting material, 77.3 grams of it would end up as the product that we want. So there's not as much waste in this process as there is in others. Okay. Right, we're going to move on to question 6 now. And 6 is in 2 parts. So there's a percentage yield question here. Okay. So we'll put in the board. So it's the mass of calcium hydroxide that can be formed by the reaction of 2.8 grams of calcium oxide with water. So I'll just summarize that a bit. What mass of calcium hydroxide can be made from 2.8 grams of calcium oxide? So the equation is that. Okay, so again, exactly like we did with questions 3 and 4, we're going to, what are you trying to figure out? So where's our question mark going to feature here? So it's what mass of calcium hydroxide? It's this one here. Just look at the name. Calcium hydroxide suggests that it might have calcium, hydrogen, and oxygen in it. And there's only one species here which actually satisfies that. Okay. And we're starting with 2.8 grams of calcium oxide. So which of these two do you think calcium oxide is? Hopefully you think it might be that one. As you'd be correct, it's got calcium and oxygen in it. And again, I'm going to set up my path exactly the same as I did in those previous questions. And I know I'm dividing by MR there, I'm timesing by MR there, and we'll do the ratio here while we're at it. So what is the ratio of this material to this material, or this compound to this compound? Well, nice and easy on this. It's a 1-to-1 ratio. So whatever number I get here, 1-to-1 will be the number I end up with here. So before I start doing any calculations, I am going to calculate the MRs of the different chemicals I'm looking at. So calcium oxide, it's got 1 calcium and 1 oxygen. So if I look at the periodic table, what does calcium have a mass of? So calcium is just there, 40, and oxygen, as we know by now, is 16. So it's 40 plus 16, 56. Yeah. It's a little bit trickier with calcium hydroxide because there's brackets. So what have I actually got here? I've got 1 calcium, and then if you've got brackets, you have to multiply by whatever is inside the bracket by the little number that comes after the bracket. So in the brackets, what have I got? I've got 1 O, okay, and I've got 1 H. But because I've got 2 lots of that, in total, I'm going to have 2 O's and 2 H's. And again, using the periodic table, calcium has a mass of 40, oxygen 16, hydrogen 1. 1 times 40 is 40, 2 times 16 is 32, 2 times 1 is 2. Add them all together. So that's 72 plus 2 is 74. Yeah. But again, I've set everything up now. Even if I've made a mistake there, or there, I will still get error carried forward as long as I do these operations correctly. So divide by MR, ratio times by MR. So, some answers. Right. So then, 2.8 divided by 56, 0.05 moles. It's a 1-to-1 ratio. So if I've got 0.05 moles here, 1-to-1 ratio, 0.05 moles there. And then I'm just going to times by 74, which is 3.7 grams. Yeah. So I've got 3.7 grams is how much calcium hydroxide I should get. And I use the word should there because in part B, it says that in the reaction, only 2.6 grams of high calcium hydroxide is formed. So part B, so this is part B, actual yield is 2.8 grams. Sorry, 2.6 grams. I do apologise. So that's what we actually got. We actually got that when we did this. Imagine we did this experiment. That's how much this chemist actually got. They should have got 3.7. So their theoretical yield, i.e. how much they should have got in theory, is 3.7 grams. So I should have got that. I actually only got that. So percentage yield is just what that is as a percentage. So let's do the calculation. So it would be black number, 2.6. In fact, I'll do it a bit up here. 2.6 grams divided by 3.7 grams. And then because it is percentage yield, times it by 100. All right. And even if you've made a mistake with your orange number, as long as you carry that error forward into this here, so if that orange number was something like, I don't know, 1,000,000 grams, because you made a really horrendous mistake, it doesn't matter, you will still get the answers. So 2.6 divided by 3.7 times 100. 70.3%. So that suggests that around 30% of our product has vanished somewhere, and it could be for any of those different reasons we looked at. It could be side reactions, could be that the reaction's reversible, it could be there was impurities in the reactants. Some of it might be lost in transfer, so pouring it from one beaker into another when you're weighing, for example. So any of those reasons is why you end up with a low percentage yield. Okay. Okay, we're going to look at question 7 now. So it's about limiting reagents, all right? I'll make this the last question today because I know that I've taken up quite a bit of time already. So we'll look at question 7, which is about limiting reagents. And again, I'm going to be using that formula triangle again. So it's 1.95 grams of potassium is reacted with 5.08 grams of iodine. Okay. Work out the limiting reagent and then the mass of potassium iodide formed. So work out limiting reagent and how much potassium iodide is formed. So I'll write the equation out and then we'll go through how we can actually do this. This is the toughest question we've done so far. So it's 2K plus I2 makes 2Ki. And it says that we are starting with 1.95 grams of potassium. And we are also starting with 1.08 grams of iodine, which is that. Well, let's say, when we're looking at this equation doesn't mean 2 grams of potassium reacts with 1 gram of iodine. This equation tells you the number of moles you need. So this says 2 moles of potassium reacts with 1 mole of iodine. So the first thing we need to do is convert both of these numbers into moles. Okay. So how do we go about doing that then? So, well, we've got masses here, which is in grams. To turn it into moles, you divide by the MR. And again, let's work out the MR of these things. So the purple one, which is potassium, goes to the periodic table. It's just one atom. It's 39. And the red one is iodine, which is 2 iodine atoms. So I'll find out what an iodine atom weighs, which is should be in group 7 somewhere. 127. So that's 254. So I've got my calculations there. I'll now perform those, and then we'll work out the limiting reagent. So 1.95 divided by 39 is 0.05. Okay. And let's work out our red number, which is 1.08 divided by 254 is 0.0043. 0.0043. I just realised the question was actually 5.08. I think that number was wrong. It's 5.08 grams. So again, I'm just going to recalculate. 5.08 divided by 54 is 0.02. That's better. Right, so now we know the number of moles. We need to see which is going to be limiting and which is going to be in excess. So one of these, this reaction will carry on until one of these two runs out. The limiting reagent is the one that runs out first. So how are we going to do this? So what I'm going to do is I'm going to just, let's call this chemical A, and let's call this chemical B. All right, and we're going to make 2 assumptions here. Let's just see what happens. Well, imagine if A reacts fully. So if all of this 0.05 moles was to react, how much of that would I need? Well, here's what we need the ratio. The ratio is 2 to 1. So it's a 2 to 1 ratio. All right. So I would need 0.05 divided by 2, because it's a 2 to 1 ratio, 0.025 moles. Well, let's have a look. Can that happen? Do I actually have 0.025 moles to react with? Well, I've only got 0.02 apparently, so we know for a start that must be wrong. So I'm going to put a line through that straight away. So let's try the other one. What if B reacts fully? Okay, so if all of B, which is 0.02, and we're going back this way, and it's still a 2 to 1 ratio, but because we're going this way, the number on this side would be twice as big, so that'd be 0.04. All right? Can that happen? Do I have enough of this to be able to react with 0.02 moles of that? So I need 0.04 moles. Do I have that at least? Yes, I do. Okay? So I know for a fact, I'm going to do a quick subtraction. If I start off with this much, and all of it's going to react, I'll end up with 0 at the end. So that is our limiting reagent. Iodine is our limiting reagent. It's the one that runs out first. And how much of this will I be left with? Start off with 0.05. 0.04 is going to react. Hopefully that leaves 0.01. Okay? So that's in excess. and this is limiting. And again, if you watch the video on limiting reagents that we posted earlier in this topic, that should help you out. All right. So the question is now, for the second part of the question, how much of this will we form? Okay. Well, we need to know how many moles of this is going to form first. So I'm just going to, if 0.02 moles of this is reacted, how much of that will form? Well, look at the ratio. What is the ratio of that to that? Big number, 1 to 2. So I'm just going to write that on that arrow. So I know if 0.02 moles of this is reacted, twice as much of this will have formed. So 0.04 moles. Okay? So I know that I should end up with 0.04 moles, but that's not the end of the question, because we were asked how much potassium iodide, i.e. the mass of it. So to work out how many grams of this thing, I need to work out, so cover up grams, I need to times the number of moles that's formed by the MR. Okay, so what is the MR of Ki? Well, it's 1K, 1I. Potassium weighs 39. 1 iodine weighs 127. Add them together, you end up with 166. Yeah, so the MR is 166. So 0.04 times 166 will hopefully give me an answer. Ooh, there we go. And like I say, this is the hardest question you could ever really be asked on this topic. But again, if you understand what this triangle represents, right, it's fairly systematic. The final answer was, so it is 0.04 times 166, 6.64 grams. Roughly, okay? So any questions, just type them in and I'll have a go.